All right. Welcome back. We are picking up from lecture 31, where we're putting some numbers to the log. Let me get the right name for that. Come on. The log stress time creep law, right? And we're using it to figure out what sort of a diameter should we design a steel rod to be if it needs to last under a tensile load for 10 years up to a particular failure strain. So we had the, let me just write some of these. Let me see if I can copy what I had on the other slide into here real quick. One second. Yay, okay. All right. So this is an example problem that's kind of tucked into the middle of chapter 13, and it doesn't even say that it's an example problem, but it is. So our job is to find the diameter of this 1030 steel rod to withstand creep up to this 0.1 inch level with a factor of safety of 1.25 for 10 years. The load is 10,000 pounds. And we're given some of these constants from that law. The capital B is 48 times 10 to the minus 38, and N is equal to 6.9. So we had changed around and reorganized the log stress time creep law to give us this equation. We define some stress, some allowable stress, failure stress, as being equal to delta divided by B times time t to the 1 over n. And so if we plug in the values that we know about this, we get sigma f is equal to, our delta was 0.1 inches. It's the maximum elongation we're allowing. And we're going to divide that by B, which was 48 times 10 to the minus 38. And then we want to get our T in terms of hours. All right, so we have 10 years, and we're going to multiply that times 365 days per year. I'm trying to figure out why they have another factor in here, and I don't know where it comes from. The exponent, anyway, is 1 divided by 6.9. They put in a 5 times 12 here. Let me just look at this for a second. I don't know where that comes from. Oh, yeah. It's initially 5 feet long. Yep. So this delta max is an elongation, right? And so if we want to put that in terms of inch per inch, it's 0.1 inches divided by 5 feet. Ah, that is it. Good thinking. Divided by 5 feet, right? Which is 5 times 12 inches. Yes, very good. So that's a creep strain, right? So it's 0.1 divided by 5 times the 12 inches. So that becomes unitless. And then we get units of PSI out of this, right? So if we put in all of those numbers, the 5 times 12 is in parentheses there, the book comes out with 23,200 PSI. So that's in a range of things we're normally used to, kind of tens of KSI. Okay. Okay. So that's our kind of failure stress. They want us to incorporate a safety factor of 1.25. So we're going to just divide that really quick. So we get our design stress, right? So it's 23.2 KSI divided by 1.25. So the design stress we're aiming for is like 18.5 KSI. Okay. And then we just solve for diameter based on the definition of stress, of axial stress, right? So this is super easy. So we just say that the design stress is equal to our load divided by the area, right? Pi times d squared divided by 4. Solve for d. So d is equal to square root 4p divided by pi times our design stress. Just check that. Yes, 4p. Take the square root. Okay. So we plug in those things, and we get 4 times the load is 10,000. Pi times our design stress was 18,500 psi. And so we get a value of 0.84. Golly, cut that out. 0.84 inches. So that's reasonable, right? So it's a fairly high load, and it's a fairly high temperature for 10 years, right? So after 10 years, it's going to be reaching that level. And I want to just calculate what that is, just for peace of mind here of knowing what so we can grow our intuition about this. Okay. Yeah, good. So that is equal to 0.00167. So on the prior plots where we talked about deriving this law, where they said that the strain values, which were inch per inch in time for things like copper, aluminum, etc., they were going up to, right, values of 0.1% or maybe a little bit higher than that. And so this value that we're taking to be our failure strain here for creep is that 0.1%.
Getting a completely different number on the allowable failure stress or whatever.
Oh, really?
Yeah.
I think she didn't convert to hour. It's just days, right?
Oh. Yes. T is time in days, it says. Say again?
The book has it, like you've written on the board.
Yeah, I mean, I took it from the book. Yeah. So the numerator,
We're getting 12.2 KSI, so.
oh, you get 12.2. So that's not that far off. So the top is kind of like 0.00167, and then the denominator, yeah, those exponents are wild here.
Why is time in days, not in hours?
I don't know. That's just what they.
Is it because of the V value?
this is just the constants that they gave us for B and N. And T is in days.
Or maybe that's why. I think I have mine in hours.
So that got for the denominator 1.75 times 10 to the minus 33.
I think the thought was I did mine in hours because he said hours earlier.
Oh, okay.
Yeah, that's what I thought.
And then we do root 6.9. I got 22,100.
Yeah, that's what I got too.
Okay, so
That's slightly off.
yeah. Probably some kind of rounding error or something like that. So it should be on that order.
Yeah, we did it in days and got that.
Okay, yeah. Okay. Yes, that would make sense because that would be 24 times longer than we calculated it for. So you would get a much lower allowable stress if it had to go 24 times longer. So the the trends anyway make a lot of sense there. Okay. So the math appears to mostly work out on this. And so we get 0.84 inches. So now you can think about how to incorporate this with what you already know, right? Of this should have a decently high factor of safety against static yielding, against fracture, and it doesn't say that it's under a fatigue load, but maybe it's 10,000 pounds in tension with a small amplitude of stress superposed on top of that, right? So you could see how for this type of a problem, we could evaluate this now for at least 4 different types of failure, and that's not including if there's already a crack in it or something like that, right? So this is another mode that we could use to see if something is failing. The rest of this chapter, chapter 13, is devoted to incorporating understanding of creep into other concepts that we already know. And so there's a little bit of math coming up, but it's in service of the first consideration they talk about is multi-axial states of stress. Okay, so creep doesn't just happen in one dimension, doesn't just happen, to axial tension samples. So if we think about what we already know of strains, we can go back to chapter 5 and think about elastic and plastic deformation in 3 dimensions. Okay, we spent a while deriving some equations for plastic strain in 3 dimensions. Okay, and so these are from chapter 5. They're okay, and here are the I'm just going to write them down. So we have principal strain. We have some sort of a coefficient out front that was related to a concept like Young's modulus or modulus of elasticity. But we can't have elasticity if we're talking about plastic deformation. So it's not E, instead it's D. And so it's some sort of modulus of plasticity. And then we combined the stresses in a similar way according to kind of Hooke's law type things. So if we have stresses in 3 dimensions, sigma 1 prime, sigma 2 prime, sigma 3 prime, we can combine them like this with some sort of a modulus of plasticity in order to get the principal strain, or the strain in that one direction. And then we can have the same thing for delta 2 and delta 3. And these are not sort of unitless values. So these are actually like the plastic deformation. Sorry, this is not the plastic strain. I should really be careful about deformation versus strain. So these are deformations. And so the difference between them is just the different combination of stresses, right? So for this one, our first term would have sigma 2 prime, then the other 1 and 3 over here, and then sigma 3 is similar. 1/2 sigma 1 prime plus sigma 2 prime. Okay, so we had something like that before, and we used it to calculate these plastic deformations, where the sigma 1, sigma 2, sigma 3 prime are principal true stresses. Oops. Okay. So we now want to incorporate time. We want to talk about rates of creep and incorporate that into these equations. So what we're going to first do is just differentiate all of these so that we get the rate of deformation, delta dot, which is just whatever our strain was, our deformation was divided by time. So it's very straightforward. It's just 1 divided by capital D. We just put a t in the denominator, and then the rest of it is the same. Sigma 1 prime minus, come on, minus 1/2 times the sum of the other principal true strains. Okay, and then we could do that for delta 2, delta 3. So we continue to sort of carry these 3 equations down. Okay. So this is helpful to us because we have an expression for the rate of deformation in time, but we don't want to have to know this modulus of plasticity in order to figure out what's happening, right? It would be really awesome if we could put in a stress here, right? And then if we can describe the stress state and some properties that we know, such as these creep parameters like the coefficient and the power and things like that, right? Then we can put that into here, and we could calculate not only the rate, but we could then calculate the length. And that's what we have when we're usually given a maximum design sort of creep strain, or we can translate that into a deformation, right? So that's what we really want. In the same way that we used before the result from a uniaxial state to then inform what we would have in 3 directions, we're going to do the same thing here in order to incorporate these. Okay. So in a uniaxial test, all we have is the sigma 1 prime, right? And we're going to give that, we're just going to keep that as some value. And then the other 2 components, sigma prime 2 and sigma 3 prime, go to 0. It's a uniaxial test. So our rate we just situation. And if we want to go to 0. And so if the plastic strains have to all deformations, all the plastic deformations have to add up to 0, then this, ensures that that is true. Okay. So we're going to use, because we're in a multi-axial state, we're going to use a concept from distortion energy. which is the equivalent stress. And so we're going to say that the equivalent true stress right, is equal to, so it's some sigma prime E, it's the equivalent stress, and it is going to be sort of a prefactor here, square root 2 over 2 times kind of the von Mises formulation, right, which was the difference between the principal stresses squared, and then we sum all of those up. And then we take the square root of that. So that's the full expression, but we're basically just talking about the uniaxial case now. So all we have is this in the first term. All we have is sigma 1 prime here, and so that's squared. And then we have a second one here, squared. And we add that together, we get a 2. And then inside the brackets, we're taking the square root of all that. So that's square root 2. And there's a root 2 on the outside, right? So that's just how it's sort of set up. So then it simplifies out to be just that. Our equivalent stress is that stress. And we have that defined from up here related to the rate of deformation. So we're going to substitute that in. So our equivalent stress is going to be the rate delta 1 dot times capital D times T. Okay. So that's helpful because we need something to substitute in for D and T. But we also had an expression before, that log stress time rule, which said that that was equal to B times sigma 1 prime to the power n. Okay. So we can write this now as, whoops, that's not the equivalent, hang on. That was equal to the rate, so we're going to substitute that in. Okay, so that's the delta 1 dot. Okay, so we're substituting that in to here, that delta 1 dot. All right, so I'm going to write that on the next slide. So we get delta 1 prime is equal to B times delta 1 prime to the n power times D times T. So now we've effectively combined into an expression what we had for our framing of plastic deformation, right, or these big deformations outside of elastic deformation. And then our rule for this log stress time rule, right, for creep. Okay. So we will solve for 1 over D times T. That's what we need for our other expression, right? So all we need to do is put that on the other side and then put the stress on the opposite side as well. And we have a combination of stresses there. So it's going to be, right, B times sigma 1 prime to the n minus 1. And because we're in a uniaxial test, we determined that sigma 1 prime is the same as that effective stress. So B times sigma prime E to the n minus 1 power. So this is now our substitution into those other equations that we had. So now we have delta 1 dot is equal to, instead of 1 over d times t, now we'll use this expression, b sigma prime e to the n minus 1. And then we have all of our sort of stress terms over here, sigma 1 prime plus, minus 1/2 times sigma 2 prime plus sigma 3 prime. Okay. We can do the same thing for delta 2 dot, delta 3 dot. So these are deformation rates based on creep rates in 3D, right, for a 3D stress state. And we plugged the same coefficient in for all of them. And so this was the same thing that we did before to derive these rules for plastic deformation. Before, though, we didn't have capital N, right? We had sort of that strengthening coefficient. We had K, if you remember. And so our coefficient was like something divided by K, and then we use that in some other equations as well, right? But here we don't have that coefficient only. Now we have something that incorporates time into this sort of effective stress. So when we used these equations before, we didn't really care as much about the rate. What we really cared about was the end result, right? So to simplify that, these same definitions, parameters, alpha and beta, which helped us to come up with constants rather than having to put so many into the equation. We came up with alpha and beta. This was on some of the problem sets and things. And so in the case of uniaxial tension, these are both 0 and things reduce down significantly. But if we take our prior equations for the rate and using the definition of these stresses, then we get these magnitudes back. So we're just we're going to integrate the rates that we had with respect to time, and they're not currently equivalent stresses and material parameters, so all it's on time. So we'll get delta 1, the magnitude of this creep strain, is equal to B times time times the first true principal stress to the 1 minus big N power. To the N. Come on, read the thing. Okay, to the N power. And then we'll have all of those terms with like our alphas and betas and stuff like that. And this is this exact same thing that we had before. So the combinations of these things, that's supposed to be a minus. Right, tell us how the stresses combine. So this is capital N minus 1 divided by 2 in the exponent. And then this is the exact same 1 minus alpha over 2 minus beta over 2. Okay. And then we can do the same thing for delta 2 and delta 3, and then they should all sum to 0 if we have, even with creep unrecoverable strain, we still have the assumption that the volume does not change. Right. Okay. The problem with this is that we talked about the microscopic origins of creep a little bit 2 lectures ago, and how slow slip in time distributed throughout some cross-section of material actually creates if you let it go long enough, it creates pores in the material, right? Or micropores or voids. They start out as voids that actually changes the density slowly of the material, which may actually have effects on the volume. But we are continuing to sort of just assume that this is a continuum solid material and that we're not taking into consideration the microstructural changes, but rather we are aggregating those weakening type things into the properties that we have, right? Like some of the measurements that are made and all these fit coefficients and exponents that come out. Okay, so that is really the limit of thinking about creep in 3D here, because all of the equations we developed for 3D are based on continuum models of stress and strain. So we can't consider the microstructural voids in these models because we're just aggregating anything into these other constants. Okay, so this is a way to incorporate that in. There are other ways to incorporate this in as well, but this is the one that we're going to use just to sort of try to get some quantified understanding for this class. So that's the section. That's the section on creep in 3D, like 3D stress states. And so after this is cumulative creep concepts. Okay, so what we just talked about was creep in the 3D stress state. And now we're going to talk about maybe a spectrum, right? So you may not have, like in our example problem, we had a tensile member loaded and held for 10 years, right? So clearly we might not have that, but rather we might have it held at 10,000 for 5 years, and then 8,000 for 2 years, and then 12,000 for 1 year, you know, and the changing loads versus time. And so the way that we handle that is we do similar to cumulative damage. We want to add up the cumulative creep deformations such that we can say, okay, if they reach some cumulative number, then we consider it to have failed. The book talks about 3 different rules by which you can do this. And they are called the time hardening rule, the strain hardening rule, and the life fraction rule. Okay. And so these are basically just how you interpret strain versus time plots and how you add up the magnitudes in order to come up with something, right? And so in this case, we can say, let's talk about the time hardening rule first. Right? So I'm going to illustrate this graphically because I'm a graphical thinker. So what we have is we have 2 plots of creep strain versus time. And so creep strain, this is going to be inch per inch. They really switch back and forth here with the variables. Okay, so they use delta for these. And then we're going to have 2 different temperatures. So temperature 1, all right, is going to be here, and it's going to be a lower temperature. So there will be some creep strain at different stress levels. Okay, so we'll call this like sigma 1, sigma 2, sigma 3, etc. So we have a suite of curves that describe the strain behavior. And then we have the same experiments, but now we're at a higher temperature. And so if I draw it, you can draw it sort of like, hang on. And these would be at these would be at either similar strain level, or stress levels, or something like that, right? And so now we can take these two plots and sort of go back and forth between them. I think I've drawn them, not the magnitudes, a little bit funny here. But what you can do is say, okay, my first phase is going to go on the lower temperature, and I'll put this in, I don't know, like blue, and it's going to go up a little bit out to some time, right? So it's at one stress level at one temperature. Okay, so that's my initial starting point. So for that phase, I can go over here and say that my change in the creep strain is equal to some value like delta 1, right? That's what I got from that phase. And now let's say I'm at the same temperature, but my stress changes. So now I'm not on stress curve 1 anymore. I'm going to go to like stress curve 3. But time is not going ahead, so I'm going to drop straight down to stress level 3. So our sequence will be, the first phase is the lower temperature theta 1 at sigma 1. So that's what we drew there. Now we're going to drop down to a second phase, same temperature, but stress level 3. And then we're going to hold for some amount of time, right, at each one. So we'll go up this curve a little bit like this. Okay. Well, we didn't go up quite as much as we did the first time. So we can just look at what that change was there and call that like, delta 2. So far, on the summary of our total strains, we've got delta 1 and delta 2 based on these different situations, and we could add them up, right, to see what our total strain will be. And we could keep going, and we could change now, instead of just swapping over to a different stress level, let's go to the higher temperature. Now in our third phase, we're going to go to this temperature, and what's stress? Doesn't really matter. We can go to stress 2, and we'll hold that for some period of time. Okay, so what we want to do is we want to pick up in time where the other one left off. So wherever we were in time on the first plot, we want to go to the exact same spot in time on the second plot. That's why this is a time hardening rule, because the time is continuous. Okay. So then we go over to stress 3, and we'd hold that for some period of time, right? And then we would calculate kind of like the delta 3 there, right? And we could do this ad nauseum, back and forth between multiple different plots, which is kind of like a lookup table. Yes?
Wouldn't this strain make more sense for time?
Say one more time.
Why wouldn't we go to the same strain level in that plot, in the different temperature instead of time?
The question is, why wouldn't we go to the same strain level instead of the same time? So that's the second rule. So these are just different ways of thinking about it. So this is a time-based rule where the time is continuous. So that's what you use to kind of anchor you between the plots. But you do have to deal with the discontinuity of the level of strain. That's why you just take the change of strain. And then you would add all of these up to come up with some total strain. And you'd compare that. And when it gets up to some maximum allowable strain, then your ratio equals 1. And you've come to the end of your life according to a prediction based on the time hardening rule for creep strains. So that's one way to think about it. The second one is a strain hardening rule. That's exactly right. So in this case, we go back and forth instead of time, but instead of then adding up the strain levels, we add up the time, right? So we keep the other one constant and then use time as our summation. So in the time hardening rule, just keep it straight. Time hardening rule, time is continuous, add up the changes in strain. Strain hardening rule, we anchor strain across the plots and add up time. And then once that reaches some total design life, then our ratio is 1 and it's met the end of its time based on that summary. Okay. And so I'm not going to draw up a second set of plots, but you could see that if I, like, I don't know, come up with another, I don't know, if I just go to black or something like that. If we went to our first phase again, and we went up to here, right, then we would be at delta 1. And if we were using the strain hardening rule, we would go to that same delta 1 level over here, and then we'd go to here and say, oh, we're there for this amount of time, right? And then what we would do is count up the amount of time that it took to go between those strain levels, and then this time here, and we'd add those time periods together, and we go back and forth based on the strain instead of the time. All right, so it's a bit of a different, it's just a flipped understanding. And then the third thing that they present to us is actually they say it's like a combination of these two, or a more holistic view, and that's the life fraction rule. And this one is a bit more complicated because it takes into consideration kind of both axes. And so I think we're going to wait until the next. Okay. And so we're going to stop there. And we're really going to talk about some examples and then other ways of incorporating fatigue in the next lecture, because we have to think about, creep. We have to I was looking at the word. We have to think about creep and fatigue. And then we get to think about ways to, and then some nice 3D plots where we talk about how things are changing in time with the mean stress and the alternating stress, and how to correctly do some of those things. So so there's a lot of different ways to combine these things, but I'm going to make sure to do at least one more in-depth example problem in the next lecture to incorporate some of these things. So the next lecture, 3 o'clock in room 102 downstairs. So if you can make it, that's fine. If not, you're welcome to watch it. And problem set 5 has been released. There's all the logistics. So I'm happy to take any questions about those things, but you guys look like you're ready to head out. Okay, thanks so much.